We derive the Laplace equation. The point form of Gauss' law is del dot D equal to rho V, where D is the electric flux density field and rho V is the volume charge density. From the definition of D, we also have that D equals epsilon E, E being the electric field intensity and epsilon the permittivity of the medium. There's also a gradient relationship which connects E with the potential through the grad operation, that E equals negative potential gradient. By putting equations 2 and 3 into 1, we have the following statement. Del dot D equals rho V. Or we have the divergence of grad of V equals minus rho V by epsilon. And this statement is called Poisson equation. Now let's look at the del squared operation in Cartesian coordinates. If A is any vector field with suitable properties, then divergence of A is this object on the right hand side. If V is a scalar function and when grad operation is applied to V, you have this vector field on the right hand side. Now the divergence of grad works out to be this object here, and this is how the del squared operation looks in Cartesian coordinates. It yields this object. Now the Poisson equation in Cartesian coordinates therefore is del squared V equals minus rho V by epsilon. The rho V is the volume charge density and it's a three-dimensional object. It's defined in three-dimensional space. If we allow at sparse or singular locations the following types of objects: point charges, which are zero-dimensional, or line charges, which are one-dimensional, or surface charges, which are two-dimensional objects, or any finitely many combinations of these three, the above three, then for such systems, the volume charge density rho V is 0. Therefore, for such systems, we have the Laplace equation del squared V equal to 0. Del squared, when applied in Cartesian, is this equation. When del squared is applied in cylindrical systems, this is how it looks. And when del squared is applied in spherical system, then this is how the del squared operation looks.